The second part of the lectures on vector calculus will be on the integral part of vector calculus. This is not as widely used in electrical engineering, kind of like differential vector calculus, primarily restricted to analysis of electromagnetic fields. So this material is mostly found in chapter 10 in your textbook. And the reason to go over this is, as I said, it primarily relates to electromagnetic fields and particularly to manipulation of Maxwell's equations. So it's an important electrical engineering concept, but it is primarily limited to fairly small specializations within electrical engineering. But it is key to understanding certain aspects of manipulation of Maxwell's equation in integral and differential form. So this is primarily just a review. We actually will not have a homework assignment on this portion of the course. So once again, you can consider this particular lecture optional lecture because we won't have homework on this. But if you would like to review integral calculus, then you're welcome to join me for the next few minutes as we discuss various aspects of integral vector calculus. So the first thing is the concept of a line integral. Basically, in a line integral, you're integrating some function along a specific curve. Sometimes the integration of a function can be independent of the path. Other times the integration of a function is highly dependent on the path. So we have some function f of x and we want to integrate it along a curve from a to b. The first thing that we have to have is we have to have some function that gives us a parametric representation of the curve. So that would be some, and in this particular example, viewing this as a function in x, y, and z as a function of time. So we have some curve x, y, and z that's specified by this equation, and t lies then between point A and point B. So A and B can be points in time. They can also be points in space, where t is a parameterization curve, where you're representing just some physical curve in space, which is typically the case in electromagnetic fields. So we're going to go from point A to point B. T is going to be a point that lies between A and B. R of t is going to be the expression of the curve. So here's an example when integrating from A to B, and then our point T would be along this length. Here's an example of a closed integral along a path. So basically A and B are equal, and we're going to close the path of the curve and integrate along the curve path. So C is a smooth curve. If you have a unique tangent, and if the tangent of the curve varies continuously along the curve. As a general case, when we look at line integrals, we want it to be piecewise smooth. So there's a finite number of smooth curves. So for example, if you had a square, that would be piecewise smooth because you would have 4 corners that themselves aren't smooth, but the pieces in between them are smooth. So a line integral then of a vector function over some curve C is basically defined by the following relationship, where you have this vector function f, and you're going to find the dot of that with c. So you're integrating along the curve the dot product of f and dr, where r of t is a parametric representation of the curve. That can be expressed as the integral from a to b of this function of r, dotted with the vector derivative, the first derivative of the vector of r times dr. So r prime is dr dt, and then dr is the differential element in Cartesian coordinates. That would be dx, dy, or dz. So here that is written out longhand, so you would have some f1 dx, f2 dy, f3 dz, where f1, f2, and f3 are the x, y, and z components of f of r, respectively. And then to do the integration, you would be integrating f1 x prime, f2 y prime, f3 z prime, dt. So if the path of integration is a closed curve, then instead of this integral along the curve, we write that with a circle around the integral to indicate it's along a closed path. We also have to assume that this curve is piecewise smooth, because then that makes this f dot r prime piecewise linear or piecewise continuous. So just a picture that illustrates a line integral in space. Here we have an r of t that's represented by the following function. Here's our f of r represented by this function. The curve is a helix, and we would integrate from a to b along the helix. So that's then done first by finding the dot product between the function of r and the first derivative of r prime of t, which is given here. So upon doing that dot product, we get the following function of t. We then integrate that dt. We can evaluate then between the two limits, 0 and 2 pi, which are our limits along the curve, and we get the following number. So that's just a numerical example of how to do a line integral in space. There are various properties for the line integral. I won't go over those in great detail. So we'll skip then to talking about independence and dependence of the path. So as a general rule, the line integral is a function of this function f, as well as the endpoints and the path itself. So obviously you can have an infinite number of curves between A and B. So you could theoretically have an infinite number of line integrals between A and B. There is a case where you can be independent of the path, and certain physical problems do follow that, where the integral between 2 points is independent of the path. So the next thing to talk about is a double integral. A lot of times we have a function that's a function of both x and y, and we're going to integrate that over both x and y. And so typically to do that, you're integrating over a region. And the easiest way to do that is to do the integration successively. So you can see here we're integrating the y part of f first, and then once that function is obtained, we then integrate that over x between points a and b. G of x and h of x here just represent the boundary of the curve when we keep x as a constant. So it's just a way to mathematically represent what's going on with f of x so that we can do the integration in the next step. Just to give a picture of what's happening, we have some region here, and we're going to integrate from a to b. And so that corresponds then to an integral in the y direction from this point to this point. So it basically we're just integrating over the region. Another useful theorem is Green's theorem. What Green's theorem does is Green's theorem relates a integral over a region to an integral along a closed path. So if we have some expression, partial of f2 with respect to x minus partial of f1 with respect to y, dx dy, where f1 and f2 are continuous and their derivatives are continuous. That enables us to take partial of x times dx and cancel that effectively, the fact that it's got a continuous derivative in x. So this is Green's function, and it's also widely used in electromagnetic fields. So basically it says that if we have a region that we want to integrate over, that can be expressed as an integral along a curved path. So here's an example of a region whose boundary consists of two parts, C1 and a C2. So in that case, we would have an F1 and an F2, and we could apply that formula shown on the previous page. So some of the applications of Green's theorem. If we have the Laplacian of W, where W is x squared minus y squared, then we can show that basically the integration of a Laplacian over a region in space R, where we have that in the xy plane, can be rewritten as the partial of that function W with respect to the normal vector times the surface differential. So ds would be differential along the closed path, where C is the path that encloses the region. So in our previous example where we had that funny kidney-shaped region, we would go from a double integral over that region to an integral along the path that encloses that region. So this can sometimes be useful. Here is an example of how to define a surface integral. You basically take a surface S. In order to have a surface S, you do have to have a function that gives you a representation of S in x, y, and z. And then once you have that, you're able to calculate the various other components. S will have a normal vector, and it'll also have a function that defines it in the plane. So you can now define the surface integral as f dot nda, where n is the normal vector to the surface, f is our function, dA is the differential element on the surface. And so if you do an integral like this, what you're actually doing is you're taking some function that's directional and you're dotting it with the normal vector to a surface. What you're actually looking at there is you're looking at flux across the surface. So if I have, if I'm interested in things like current densities or electromagnetic fields, and I enclose a surface and I do this particular kind of integral, then I'm looking, in the case of an electric field, I'm looking at the electric flux through the surface S, or through the region S, through the region R that would be enclosed by some closed path. So you can basically do that in terms of angles between the field lines and the surface normal, and so and then you can relate those to x, y, and z coordinates. So out of that particular integral, you get the following expression, where f1, f2, and f3 are the x, y, and z components, respectively. It's also possible to do a triple integral. Triple integrals are important in the divergence theorem. So if we take the divergence of some vector function f that was given in the previous chapter, so this is the expression for the divergence. Gauss's theorem says that the integral of the divergence over a volume is the integral over a closed surface of f dot nda. So this is useful for looking at things like the divergence of fields over a volume, say electromagnetic fields over a volume, so we're looking at things that are enclosed in space. A useful thing there is that if we look at a volume integral of something like an electric field, because charge can neither be created nor destroyed, once we choose a volume or a volumetric region in space, we block down the amount of charge that's present in the region. So this relates directly to some of Maxwell's equations, and it allows us to take a triple integral over a volume and reduce that to that vector dotted with the normal to the surface area. So for example, if your surface is something like a sphere, then this becomes an easier integral to do. So once again, related to angles between the normal and the vector, you can get a series of expressions that look more complicated than they are. And then that leads us to solutions of Laplace's equation. So remember that our field F can be the gradient of a scalar. So if we go back, if we then substitute the gradient of the scalar in for F, we get the divergence of the gradient, so we get the Laplacian. Also, if we have the normal dotted with F, that's basically the normal dotted with the gradient of the scalar. So if we look then at what that means with regard to a volume integral, that means a volume integral of the Laplacian is equal to the integral of the Laplacian, the derivative of the Laplacian with respect to the surface vector, the surface normal, over the enclosed area. So this is just a property of solutions of Laplace's equation. Laplace's equation is an extremely important equation in electromagnetic fields. The final thing to look at is Stokes' theorem. Stokes' theorem is another thing that relates surfaces and lines. So the curl of a vector function is given by the following determinant. Stokes' theorem says that if we have a surface integral of the curl of f dotted with the normal over some area A, that's basically equal to that surface dotted with the parametric representation of the curve that encloses the surface. So that vector dotted with a closed path that encloses the surface in the double integral can now be reduced to a single integral where we're looking at closed path. So this is commonly used in electromagnetics and current to determine solutions to Maxwell's equations. So once again, the use of vector calculus and integration is pretty much limited to the solution of electromagnetic fields problems. At one time, we had courses in graduate electromagnetic fields. We no longer offer those in our department, but if you want more advanced treatment of this, there are a number of textbooks that you can look at that'll show basically how vector calculus is used to solve electromagnetic fields problems. Fortunately, in electromagnetic fields problems, there are a lot of symmetry. So these dot products and cross products, divergences and curls, if you set the problem upright and choose the right coordinate system, often you can make 2 or 3 components go to 0, which greatly simplifies the mathematics. So the x, y, and z Cartesian coordinate system is often generalized for either polar or spherical coordinates, cylindrical or spherical coordinates, which makes the math of the problem align with the symmetry of the physics, which makes a lot of the components drop out.